For timber structure, we've got a diverse timber selection to choose from. We can use sawn timber like SG8, and we can use LVL, or we can use glulam such as a GL8. Of course, you have a GL10 and GL12, etc. Um, so a little bit of recap of those materials, because so for SG8, normally you would see this material has been heavily used in residential area that used for joist and dry walls, which is the timber framing, and you wrap it up with a gyp board, gyp plaster board, and for floors you've got your plywood over, and at the bottom you've got fire line sort of gypsum board to line it up. So these members are typically being covered in the wall, it's so-called dry wall. And for so this it comes with a normally it's cost effective if you're using SG8. Of course, it is SG10 and SG12 as well, not that commonly to be used. Because if you tend to use those higher grades, you would naturally jump into try LVL whether it works or not. So LVL comes in different um, grades as well. You got an LVL 10 and a 12, and so forth. So for the LVL, the manufacturing process is slightly different because the sawn timber just cut out from the timber block, and for LVL, and you can see it's multiple layers of veneers. So those little thin piece of the veneers is just being peeled from the lock. You've got normally the round lock goes into machine. There's a rotary peeling process that cuts the lock in a thin layer, and it cuts over and over and over. Then eventually it gets that stretched up. Then you cut it in shape. You pressed it, hot pressed it, and glued it, and then cold pressed it. So those kind of process makes the LVL. So because of that, and the only thing that you notice that is when it comes to the bending moment and the capacity design, and those material reduction factor 5 for sawn timber and glulam, they're all 0.8, so the 20% reduction of the strength. But when it comes to LVL, it's only 10% reduction because the process of making the LVL is more the material is more predictable, less uncertainties. That's why it's got a 0.9. So very good in terms of the strength. And also you can see the bending strength is about nearly 2-3 times, 2.5 times more than the sawn timber SG8. So in terms of bending strength, it is quite good. It is really good in bending and shear as well. And next, the weekend comes to the glulam timber. So glulam timber is just layers of the sawn timber that has been glued together. In this case here, this is called a PLT because it's a parallel glued timber. And also you've got a CLT as well because you've got those timbers cross the laminated on each layer. So we'll talk about that in the CLT design. So in this case here, we've got 3 different types of beams, and that mostly used in the timber structure. We've got a sawn timber, we've got LVL and the glulam. And the price wise, that's what I normally first to take a job on, and I would be thinking what would be the price, what would be the cost for the job. So normally I would go starting from for typical job, small job, I would go for starting from the SG8 where this gets work, and giving that the structure is going to be wrapped around with gypsum boards on plywood or anything. You don't see any of this timber exposed. And if it structurally does not work for a beam, for example, for a beam or lintel, and I'll jump into the LVL. And LVL gives much strength and a higher stiffness because you can see the elastic modulus is 13,000 compared to 8,000. So I would jump onto next stage. It would be jumped onto the LVL to see whether structurally make it work. And the only thing that I would use glulam timber is when there's a high end residential or high-end project that has come with premium architectural aesthetics. And that also comes with some architectural features that I want to express. For example, you want a glulam, because the glulam here, to expose the glulam would certainly make your projects more appealing. So that's when you want to expose your structure, you would use glulam. Otherwise, anything you wanted to wrap it around, I would more lean to SG8 or LVL structure. So price-wise, so SG8 is the cheapest. You get about, I don't know, but today is roughly about $1,000 per cubic, plus minus, I don't know, 100 to 200s. And LVL comes double that, and it's just at the ballpark figure. And the premium price would be glulam structure, and the glulam comes in nearly 3 times more than sawn timber. So that's just the ballpark figure that allows you to think of the project's budget. Think about client's budget, and just to be able to communicate the cost at the first start with architect or clients that'll make a good start. So in terms of design of the bending strength, so the formulas came out from the NZS 3603, and you can do it with 1720 if you like. It's the same thing. The only difference is these key factors. There are many key factors here. For me, I would just say this is a big K, and these big K comprises these small Ks, K1, K4, K5, K8, etc. Every design of the bending capacity, you would involve a material reduction factor, which is 5. For bending is 0.8. As I said before, for LVL is a exception. LVL is 0.9 and the glulam is 0.8. And the rest would be the bending stress of the character, bending stress of the material. So these are the came out of the manufacturer. The specs, the different suppliers may have different values for their characteristic stress. So you have to make sure you check those stresses before you put it in. They are not the same. Then you will be your section modulus. So that'll be straightforward. BD cubed over 6. And then your K1 factor, that is load duration factor. Okay, and then just check those that according to the 3603. And the K4 factor, that's depending how many members you have. For example, if I've got 2 SGA members side by side, I've got 2 members. And for a starter, minimum 2 members gives you increase your strength by 14%, so 1 times 1.14. But for the LVL and the GRA, I'll sometimes just say, I'll take as 1, just being conservative sometimes. K5 factor usually is not great system, and K8 factor as well. K8 that comes to play. So K8 is a lateral torsional factor. So when a beam is trying to bend, it's not going to be. It is going to bend like a sagging vertically, but also what it does is behaves like a trying to kick back. It's called lateral torsional buckling. So what normally your beam would have a plywood on top, there's a flooring on top, or you have your joist that is running perpendicular to it, provides some lateral torsional restraint. So in this case, you can calculate your K8 by using this equations here. So you would have your bending about your major axis, which is XX, and then your minor axis, which is YY. So for major axis, it's normally between the supports. That will be the full length. Major axis would be 4. And in this case here, we are worried about the bending towards the minor axis. So what are the elements that is restraining the minor axis from twisting, from rotating? So in this case, we've got a joist at 400 centers. So these joists are providing the lateral restraint to my beam. So that means our LAY is going to be 400. That is the distance for LAY. The definition, that is any elements, the structural elements that are providing the restraining to the lateral torsional. And then my LAY divided by the breadth of the beam is 90. I've got a double, say I've got a double 240 by 45. So 400 divided by 90, 4.5. And then from the 4.5, I can looking at the ratios here. So I've got that is in the ratios of 4.5 is quite small, something over here, right? And my depth to the beam ratio is 2.7, somewhere around here. So it's not reaching this curve yet. So you can see that your K8 factor is 1, is typically 1. So that means your beam is quite stable, it's rigid, it does not trying to twist or rotate. So this is the K8 factor needs to pay attention to. That's important when it comes to bending design. The rest would be just the typical K1, K4, K6, and so forth and so on. Just be mindful when you do design for LVL and a GL8, your K24, the value comes in play. That accounts for the size vector. The deeper you go, and the smaller bending capacity you would have. That is considered as a size factor. And for some manufacturers, for example, here I'm using the high span beam, the Carter's product. So they have a specified reduction factor of that. So 95 divided by the depth of a power of 0.152, 154, sorry. That gives you the K24 factor to be 0.87, so 13% strength reduction. But for LVL, if you look at the code, it says anything if it's less than 300, it does not get reduced. So it's still going to be K24, still going to be 1.0. So that's the bending design of the timber beam. Thanks for watching.